Greetings students. In continuation with our chapter Electrostatics, last class we have discussed about what is electric dipole. We have discussed about the field of electric dipole, and we have derived the formula for any point on the axis of dipole. Okay, the electric field on any point on the axis of dipole. So in today's session we'll continue. So the electric field due to electric dipole. Okay, we'll find out this. First we have discussed about on the point of, we have already done that for the point on the axis of dipole. Okay, so today we'll discuss about for the points on the equatorial plane. Okay, first we'll draw that what is dipole. We have one positive Q charge, we have another negative Q charge. Both are 2a distance apart. Now we'll make a equatorial plane which is perpendicular to the axis of dipole and passing through the center of dipole. We have a point P on it, on which we have to find the electric field. Let's say this point is r distance apart from the center of dipole. The direction of dipole is minus q to plus q. Okay. We have an electric field on point P due to plus q charge, that is E plus q. We have electric field due to minus q charge at point P, E minus q, and that electric field is in the line which is meeting this electric field in the line which is connecting plus q, my apologies, which is connecting minus q and p charge. My apologies. The electric field on P point due to plus q charge is in the direction away from the plus q charge and along the line which is meeting plus q charge and point P. The electric field E minus q due to minus q charge will be along the line which is meeting minus q charge and P point, and the direction of E minus q will be towards the minus q charge. So we have to find the net charge, okay, the resultant of these two, okay, which will be, because E plus q and E minus q both are equal in magnitude, okay, so the resultant would be in the direction which is opposite to direction of dipole, okay, and that will be given as E, okay, at P point. So the magnitude of electric field fields due to charges plus q and minus q are given by E plus q equal to kq upon the distance between P point and plus q charge and minus q charge. So the distance is r square plus a square. E minus q will be given as kq upon r square plus e square. This is just the magnitude. If we take the component of these two electric fields at point P, the component which is normal to the direction, which is normal to the dipole axis, will definitely cancel away. Okay, the component of this will be which is perpendicular or normal to the direction of dipole axis will cancel away, will be cancelled, and the component along the dipole will add up. So the total electric field will be given as, if we show the direction also, then the net electric field, the total electric field at P point will be given as E plus Q plus E minus Q cos theta opposite to direction of dipole. So minus sign will come and the direction of dipole P cap will show like this, because the total electric field or the resultant electric field is opposite to P cap. Okay, so the same will be given as EP vector equal to minus QQ upon R square plus A square plus KQ upon R square plus A square into cos theta P cap. So EP equal to minus 2KQ upon R square plus A square. Now with the diagram, the cos theta, where the theta is angle made by the position vector of P point from any charge with the axis. Okay, so if there is a line which is meeting P and any charge, like let's say positive Q charge, then the position vector or position vector of P point with respect to the positive Q charge, okay, and we have the dipole axis. So these two lines making an angle theta with each other. So with this diagram, the cos theta will be based upon hypotenuse. So cos theta will be written as A upon hypotenuse, which is R square plus A square whole power 1 by 2. So EP vector will be given as, we can write K as 4 pi epsilon naught 2 QA upon 4 pi epsilon naught into R square plus A square whole power 3 by 2 into P cap. So this will be the electric field given at any point on the equatorial plane of a dipole. Now at a large distance, when R is greater than A, we can write the electric field EP at point P on the equatorial plane of the dipole as EP equal to minus 2QA upon 4 pi epsilon naught RQ into P. From this equation, it is clear that dipole field at large distance do not involve Q and A separately. It depends on the product of QA, and from this we can get the definition of dipole moment. From here we will get the definition of dipole moment. The dipole moment denoted as vector P of an electric field, my apologies, of an electric dipole is defined by E vector equal to Q into 2A multiplied by T cap. So it is a vector whose magnitude is charge Q times the separation of 2A between the pair of charges Q and minus Q. And direction is along the dipole along the line from minus Q to plus Q. So we can write the above equation of EP as follows. EP vector equal to minus P upon 4 pi epsilon naught RQ, where R is greater than A. So this is what we have derived: electric field due to electric dipole for the point of equatorial plane. Now the point is, the magnitude and direction of dipole field depends not only on the distance r but also on the angle between the position r and the dipole moment. We can think, when let's say 2a, the dipole size is approaching 0, the charge q approach infinite in such a way that the product of p, that is dipole moment q into 2a, is finite. Okay, such a dipole is referred as point dipole. Point dipole. So it is a definition of point dipole when the size 2a approaches 0 and the charge q approaches infinity, in such a way that the product, that means dipole moment p equal to q into 2a, is finite. Okay, in next session we'll discuss about physical significance of dipole, the dipole in a uniform electric field. Then we'll go with the Gauss law and we'll study about different cases of Gauss law. Thank you.